Okay, so in the last example we learned how to use this equation here, and then we talked about these equations here, but we didn't really do an example with them, so let's do one now. So again, we've got P, which is a power, which is a rate of energy transfer. Sorry, I'm pointing at my screen and you can't see me do that, but that's alright. P is power. It's a rate of energy transfer, so we have Q divided by T. It also can be written as Ka delta T over L, where K is thermal conductivity, A is an area of thermal conductivity, L is the thickness of the material that's conducting heat, and T is the difference in temperature. Once again, K, thermal conductivity, is a material constant that's different for each material, and we'll talk about how to use that. So we need to calculate the energy transfer in a wall section that is measuring 2 meters by 1 meter by 0.04 meters thick with a thermal conductivity of 0.1. Opposing sides of the wall section have a temperature of 10 degrees and 5 degrees C after 1 hour. So there's a picture over here showing us that, and we can use this to solve all of this to solve for our energy transfer. So let's look at that again. Energy transfer was, well, we'll get to that later. It's not letting me go back for how I'm recording this, so we'll get to that in a bit. All right. Just as a side note, this type of example will be used in your practice problems to do the top of an acrylic box, and you're just looking at the top, the insulation on the top. So it's going to tell you about a 3/16 inch wall and 1/2 inch insulation and all that jazz. You're only worrying about the area and the thickness of your insulation, not the walls themselves. We're only worrying about insulation. So something to keep in mind for future reference. Okay, so our area of thermal conductivity would be this wall over here in the top right, and it's 2 meters by 1 meter. So since it's a rectangle, the area is just 2 times 1, which is 2 meters squared. Our thermal conductivity, one thing that you can use to make you know you're in the correct units are these constants. So this constant is in joules per second per times meters times degrees Celsius. So you need to know that all of the rest of your information needs to be in these units right here. So I'm in meters. Even though it's meters squared, I'm still in meters, and we're good to go there, okay? Something to keep in mind also for future reference. All of your units need to match. Thickness of our material, L, is 0.04 meters. Difference in temperature, 10 degrees to 5 degrees. It's a 5-degree change in temperature. And difference in time, it tells us 1 hour. However, our constant tells us we should be in seconds. 1 hour is 3,600 seconds. If you don't know how to do that conversion, something to figure out, and we're not going to talk about in this example here. Okay? All right. P is the rate of energy transfer, and Q is the energy transfer itself. We are looking for the energy transfer itself. In the equation that we were given, we know that P is equal to Ka delta T over L, and it is also equal to Q over delta T. So because these are both equal to P, we can set these two equations equal to each other. I can set this equal to this, and we can solve for what we need. So let's do that. So they just combined equations in terms of Q, and so when I do that, if Q is P times delta T, what they did here is they rearranged this equation right here in terms of Q, and then they plugged in, for P, they plugged in this equation here. And so that jumps down here, and we end up with P times delta T to get Q. Okay. So, rewriting it again, we just take our givens. Now that we've rearranged and done all of our equations, it's pretty straightforward. Ka delta T over L times delta little t, which is time. So 0.1 joules times seconds times meters times times degrees Celsius times 2 meters squared times 5 degrees Celsius, all of that multiplied together and then divided by 0.04 meters. That whole product there should be multiplied in the end by 3600 seconds, and that gives us 90,000 joules, which I assume is probably a rounded number because that's how they like to do things for whatever reason.